Okay, this is lesson 1.1, relations and functions. In this video, we're going to compare relations and functions, and we're going to introduce something called domain and range. First off, what is a relation? Well, a relation just describes a relationship between a set of information. So commonly, it's an X related to a Y, and we can represent this in a bunch of ways, some of which you've already seen. A function is a specific type of relation where each X has exactly one Y. So in the relationship, if you're given an X, there is only one Y, or only one answer. All functions are relations, but not all relations are functions. And then second, we're going to look at domain and range. Domain is just a way to describe the set of all the possible values of X. And range is a way to describe a set of all the possible values of Y. X being the independent variable and Y being the dependent variable. All right, so let's get started here with set builder notation. What is a set? Well, a set is just a collection of things or elements that are listed. So for example, if I wanted to build a set of my favorite TV shows, I could name my set whatever letter I want. So I'm going to name this set A. So I'm going to say A is equal to, and then we use this nice cool bracket that I am terrible at drawing to open the set. And inside we can write all the different elements or all the different things that are in the set. So what are some of my favorite TV shows? Well, we must first start with my favorite TV show of all time, which is Seinfeld, and then include some more recent ones like The Office, and let's say one more. Let's go with The Bachelor. And if these were my only favorite shows, I would close my set. They aren't, but for this example, let's say they are. Let's say I only have 3 favorite TV shows, and it's Seinfeld, The Office, and The Bachelor. Another way you can describe a set is by writing it according to rules, and that's called set builder notation. So I'm going to show you an example of a set builder notation. In set builder notation, we use the same type of brackets, and we're going to describe all of our X's belonging to a certain type of system of numbers. So moving away from the idea of TV shows and moving into the world of math and working with numbers, we're saying here that X belongs to Z. This symbol right here is the element symbol, and it just means belongs to. What Z is I'll show you that in a second. And this is just saying X. So this says X, and then in words is an element of Z. And what's Z? Well, Z is a type of number system. And there are several types of number system. There are natural numbers, and for natural numbers we use the letter N. For whole numbers we use W. For integers we actually use Z. And the reason we use Z is because I was taken. I stands for imaginary, and when we look at imaginary number sets later in the course, we'll use I. Rational is Q, and the reason it's Q is because, well, R is taken by real, R. What do these numbers mean? Well, natural numbers is the set of numbers that are counting numbers. So the numbers you first learned when you were learning math, numbers like 1, 2, 3, 4, and so on. All the numbers you can count. You can count parts of wholes, but for the number set, natural numbers, it's just whole numbers. So 1, 2, 3, 4, 5, and so on. And we can close that set. Whole numbers, pretty much the same as natural numbers, but it includes 0. So 0, 1, 2, 3, 4, and so on. Integers is pretty much the same as whole, except it also includes negative numbers. So if we start at -2, there'll be numbers before that, -1, 0, 1, and 2, and so on. Whole numbers, but including negatives, that's integers. Rational is all the integers and fractions as well. So anything you can write as a fraction. So I'm not going to write this one as a set. I'm just going to say fractions. plus integers. And real numbers are any number that you can actually write. So that includes fractions, integers, and then things you can't write as fractions, like pi. So any number, decimals, fractions, and integers. So why have these number sets? Well, if we're writing a domain or a range or a set, we want to try to describe it as simply as possible. And if you have only a couple things, you just list them. But when you have a wider range, you may choose to write it using set builder notation. So let's see what we've got here. So far we know that x is an element of, and this one says integers, z. Z is integers. So that means that all of the things that x is has to be an integer. So it has to be a negative or positive whole number or 0. And then this vertical line here means such that. Such that x is, if we read to the left, greater than -2, and if we read to the right, less than or equal to 5. So x is between -2 and 5, but x does not equal 3, so it's not 3. That's what it means. So this set are the conditions. So let's list them out. This is set builder notation. Over here I'm going to rewrite this set and we're going to include all the numbers that are actually in the set. So -2 to 5 but not 3. So that would be -2, -1, 0, 1, 2, 4, 5, not 3. These things are equivalent. This is a set, and this is using set builder notation. What's easier to write? Set notation. It's easier to just list those 7 numbers. But set builder notation is a way to describe a huge range. When you're working with integers, you're probably not going to use set builder notation unless you're listing like 100 different integers, and then it's probably easier to write it using rules. We're going to get some practice with that. We're also going to get some practice with sets. All right, so now that we know what domain and range are, and we know all the numbering systems, and we know how to write a set builder notation and a set, let's discuss whether or not something is a function or a relation, and then try to write the domain and range. So I'll try to keep this on here for the first couple of examples. And here we go. To identify a function, relations can be represented in various ways, and it's important to be able to identify which relations are functions in each of these representations. The first set of representations are ordered pairs, table of values, and words. So in order for a relation to be a function, each x has to have only one y. Relations can have x values with 2 or more different y values. So let's take a look at our first set. And here we have a set of points. 1, 2, 3, 4, 5 different points. And we have to decide whether this is a relation or a function and then write the domain and range. So let's take a look. We've got -3 is an x and 0 is a y. -1 is an x and 1 is a y. 0 is an x and 1 is a y. 4 is an x, 5 is a y. 0 is an x, 6 is a y. And what we're doing is we're looking through this set to see if in there's an x value that has more than one y value. And if we look right here, 0, 1, and 0, 6. This set is a relation. And the reason is because x equals 0 has 2 values of y. 1 and 6. In this relationship, 0 can equal 1 or 6. So it's not a function, it's a relation. To define the domain, what we do is we look at all the different possible values of x. And we've got -3, -1, 0, 4, and 0 again. It's probably easiest just to list those as a set and not use set builder notation. So our set for the domain is -3, -1, 0, 4, and since 0 is listed again, we don't have to list it again in the domain. So those 4 numbers represent our domain. Our range is just the y values. And our y values are 0, 1, 1's listed again, so we don't have to write it, 5, and 6. And it's common practice to write them in increasing order, just for organizational purposes. So here we go. We've got a domain of those 4 numbers and a range of those 4 numbers, and this is a relation because x had 2 values of y. If we're looking in a table, let's move down, same idea. To decide whether it's a function or a relation, we're looking to see if there's any x value that has more than one y. And -2 is 4, -1 is 1, 0, 0, 1, 1, 2, 4. Each x has only one y. We have repeated y values, but that's okay because they came from a different x. So this is a function. For the domain, we just list all the values of x. So -2, -1, 0, 1, 2. And for the range, we list the values of y. So we've got 4, 1, 0, 1, 4. So 0, 1, and 4. My parentheses already look terrible, but that's okay. Last example. If x equals 1, then y is 2 or y is 4. So right here, what we're defining is we're defining a relationship in which this x has 2 different y values. So that makes this a relation. And for the domain, we just have one x, and it's 1. So we just list 1. And for the range, we have 2 different y values, 2 and 4. So our range is 1, our domain is 1, and our range is 2 and 4. There's another side to this where there's 3 more examples. What you can do is you can pause the video and you can try those, or you can wait till the end of the video, come back and try those ones on your own, and the answers are posted on our course website. Another way we can show a relationship is by creating a mapping diagram. And in a mapping diagram, you put all the elements of x, or in the domain, in one bubble, and all the elements in y in the other bubble. And to show the relationship, you take the value of x and you connect it with an arrow to the value of y. So in our first relationship, what we have is our x's, -3, -2, -1, 0, and 1, and our y's, -6. And all of these x's are mapped onto the same value of y. So no matter what our x is, we only get one y. So does this make a function or a relation? Well, since each x has only one y, even though it's the same one, this is a relation. Nope, that's wrong. This is a function. Sorry, a function because each x has only one y. For the domain, we could just list all the x values, but we worked with that set builder notation, so let's try to write one using set builder notation. You have the choice to do whichever you want. Usually you do the easiest, and it would be easier just to list those 5 values. But I'm going to show you what set builder notation looks like. The range is just one number, so I'm just going to write the number, -6. For the domain, we can start by saying our domain is x's, so we're going to say x belongs to, and we have to choose our number set. So if we remember our number sets, which one includes negative numbers, 0, and whole numbers? That would be integers. So x belongs to integers, and then vertical bar such that, and now we're just writing the range of numbers. And to do that, you write the number furthest to the left on the number line first, and that would be -3. And furthest to the right, I'm going to leave some space and write 1, and then close my set. This is x's, so I'm going to put x in the middle. And then using less than signs, you put a less than sign here and a less than sign here. And you read from the middle out. So if you read from the middle x to the left, it would be saying x is greater than -3 and x is less than 1. So that's covering the whole range, but it also includes -3 and 1, so we write an equal to as a part of this sign. And there's a set builder notation for the domain. You can try B on your own, decide whether it's a relation or function, write the domain and range. You can use set builder or set notation, up to you. All right. Example 3, graphs. When looking at a graph to decide whether it's a relation or function, you can do something called the vertical line test. And what the vertical line test is you simply draw a vertical line across the graph, and if anywhere on the graph it hits the graph twice, and by graph I mean the relationship, so in this case we have a sideways parabola, if it hits the relationship twice, it is not a function, because that means for that x there would be two y's. So let me show you what I mean. If I draw a vertical line over here, I don't actually hit the graph at all. So not really a good spot to do the vertical line test. But if I draw the vertical line here, I hit the graph only one time. Because when x is 0, y is 0. So for that x, there is only one y. So that would make me think it might be a function. But if I draw a vertical line here, I hit the graph here, and I hit the graph there. If anywhere on the function, or relation, sorry, if anywhere on the relation you hit the graph twice, you fail the vertical line test. And that means it's a relation. It is not a function. Let's see if we can come up with the domain and range. We got some arrows here to show that it continues. For the domain, we're trying to describe all the values of x. So, x here, and the function seems to, relation seems to be going to the right. So starting at 0 and getting bigger on the number line. And it's not just points, so it includes everything along this curve. And as soon as you have a connected curve and you're including everything in between, that's the biggest number set there is, because that includes all the decimals, all the decimals, all the fractions, all the integers, all the whole numbers. That includes everything. So that's your real numbers. As soon as you have that curve and you're connecting everything in between, like if we look at numbers on this curve, we've got 2, and this would be 1, and that'd be a half, and in between a half would be like a quarter, and we can get even smaller. There'd be decimals, like repeating decimals in there. Everything is included on that curve. So that would be real numbers. And since it's not just points, we can't just list all the x's. So we actually have to use set builder notation. And we have to say that x belongs to real numbers. Such that, and now we have to define this curve. So x looks like it's bigger than 0 because it's going this way. It also equal to 0 because we have a point right there at 0. So we say x is greater than or equal to 0. And it continues because we're continuing with an arrow, so it just keeps going. So x belongs to real defines everything in between, but x is greater than or equal to 0, starting at 0 and going to the right. Range. Range is y's. So let's see what y belongs to. Well, y belongs to, if we go up, we're still connected with this curve and we're going up. So we're including everything between, and we're going up past 2, and it actually continues going up forever and ever and ever, so we're going to keep going up. It also keeps going down forever and ever. And there are points between there, like 2 is here, but 1 would be here on the y scale, and then a half would be like right here, a quarter, and we've got all the decimals in between as well. So we've got real numbers again. And since we're going all the way up and continuing up, and all the way down and continuing down, there actually is no other condition here. It's just y belongs to real numbers. It's definitely bigger than 0, and it's below 0, and that's really everything. So y belongs to real such that we don't actually have to write any conditions. So I shouldn't have written that such that sign already. We can just say y belongs to real numbers, and there are no restrictions to that. It's just y belongs to real. Try determining whether this is the function or relation, and the domain and range as well. And you can check your answers on the posted document online. Last one, equations. In order to decide whether a relation is a function, we know that each x has to have only one y, and if you have an equation, there's a couple ways to do it. You can create a table and sketch a graph and then see if it passes the vertical line test. You can recognize a common equation and then think about what the resulting graph would be like, and then decide whether that would pass the vertical line test. Or you can look for terms that have y squared. And if you have y squared terms, that means there's going to be multiple y's for each x, and that would mean it's not a function. So here's a couple. We've got y equals 2x minus 5. What type of equation is that? Well, that's like a y equals mx plus b. That's the equation of a line. So this is a line. And as long as it's not a vertical line, we're probably going to pass the vertical line test. And this is not a vertical line. This is a line that goes through negative 5 at the y-axis, has a slope of 2. So that's a line that looks like this. And lines, if they're not vertical, are functions. And if we have a graph that's going up and down, left and right, and there's no restrictions on that, our domain is x belongs to real. And our range is also y belongs to real. Because on a graph, if I were to graph this line, I'm going to sketch it. Starting at negative 5 and having a slope of 2, we've got a line that looks like this. We don't have any restrictions. On the x-axis, we're going left to right forever and ever, and we're connected with the line. So that's real numbers. And we're not starting from somewhere and going to somewhere else. We're continuing forever and ever, left and right, up and down. So that's no restrictions on the domain or the range. X belongs to real and y belongs to real are pretty common for domain and ranges of functions. There's certain functions that do have restrictions, but when you're looking at lines, x belongs to real, y belongs to real is the domain and range of almost all of your lines, unless it's a vertical line or a horizontal line. B, I'm going to get you to try on your own. Try to remember first what type of function that is. I'll give you a hint. It's a circle. Sorry, and not function. It might be a relation, but you can try that one on your own. Be sure to finish the ones that we didn't finish on the video lesson, and check your answers by checking the document on our class website. And thanks for watching, and I'll see you next time.